the next time, the next session is the breakout section, which you can also all join and discuss whatever you want to discuss. But I think we should call an end to the panel, this panel, just to keep the program moving. That's
okay. Thank the panelists.
That's good. I would like to.
Very nice.
Okay.
Thank
Yeah,
you.
so it's 10 minutes of break time, but we also have Ask Me Anything guests and hosts, and you can chat for the first one. Well, maybe let the host start.
Hi, how are you? Can you hear me? This is Jorge. Oh, can
Yeah,
you
hi.
see
Hear
me?
you, but I can't see you.
Yeah, I see. I know. Yeah, let me see. Can you see me now?
Better.
Not
Later.
Oh, okay. Let me.
Look perfect.
Can't make out, but yes. we can.
Maybe yeah, I'm hiding some of my. So is my guest around? I want to.
Yes, I'm here.
Hi, how are you?
Fine, fine, thank you.
Okay, so I don't
Also
know. If
getting
you,
dark here in
I don't know if after listening to all this discussion about why programmers or software engineers, let's say, don't know they don't know how to even see or describe or what an invariant is. I don't know if my question matters. I had a question for you that was a little bit more related to what you do and in general, and I guess there are experts here that do verification and specification. And my question was more in the general sense of how you do randomized algorithms specification and verification. How far are you in that area? Probabilistic algorithms in general. I want to know if you have thought about it. I was looking at the program on a Splash, and there is an invited speaker that is going to talk about Julian, and Julian is going to introduce a small, I think, derivations in the programs, and also you can put pieces. There is other languages, and you can put neural networks in the middle of your sequential program. So, we are moving even higher. So we are complaining here that we don't know how to write sequential programs and how to write specification. But people are doing extremely complicated things, and life goes on. So I don't know. This is my general thoughts about.
Sometimes.
Yes, I'm afraid it's something, yes, I've thought about, I'm interested in, we're working towards it, but I'm not using probabilistic.
But what do you think about how it will take? I am not, how you will go around. So I want to prove I use programs. There are many programs, distributed programs that have to be random, have to be randomized. Otherwise, solutions don't exist. So how we can do these kind of things?
Yeah, maybe I'm the wrong person to ask this kind of.
Anyone can answer.
But maybe, I mean, you were first asking what I'm doing.
We can also, other people can ask Michael Leuschel question too, right? Michael is a good continuation. He is expert in TLA also. He does Pro-B and all these system specification.
So maybe like a politician, I might just turn back to the previous talk and say something about invariance.
Sure.
Go for it.
So I agree that invariants are important and can save you time. So I'm currently working, for instance, applying formal methods to safety critical systems and reasoning about railway signaling algorithms and new algorithms to guide trains more efficiently. And I see people in the industry works a lot still by specifying behaviors. And as I think it was also Leslie said, that's a bad way to reason about a system. And it's very hard or almost impossible to get these complex systems correct. And you fix one behavior and then you break another one and you never really reach a completely correct algorithm. And one tool, I think the only real tool that works, that scales, is finding an invariant, finding why your safety critical system is correct. And it's related also, I think, to abstract interpretation. Quite often an invariant is a kind of an abstraction. You have, for instance, in train systems, you have an envelope that a system maintains surrounding a train, and it's an invariant you have to keep, that the real train is within your envelope, and you have to prove that every step of your train control system or algorithm preserves that invariant. And I think it's the only way to develop a really correct system, and it has to be taught. And we're doing it baby steps, bringing it to industrialists, and I think they see the value because they have hard time maintaining their systems. Too much energy goes into testing and fixing bugs, and yeah. So that was one answer. Going back to what I'm doing is also is building tools for formal methods on using Prolog as a programming language, but for modeling the systems, I'm using first order logic and the B language, which is quite similar to TLA, I hope. And there are a lot of...
That's a tough question.
There are a lot of systems properties that can't be expressed merely using variable invariants. I mean, things, and it's very difficult to try to force them into variable invariants.
Yes.
And from the point of history, it was Turing who actually did first prove the program using variable invariants. So he's the godfather of it. And I just want to mention that over the chat thing, there's an interesting discussions going on, just not by me, but other people making interesting points like Patrick. So some of you might want to take a look at the chat. And also, I think what is fundamental is what is logic programs? And when Planner introduced logic programs, it did both the forward chaining and the backward chaining. And Prolog only kept the backward chaining. So I have a proposed definition. I know that Bob disagrees with this, so he might want to chime in. What is a logic program? And what I say, a logic program, you have to justify every logical step with a logical rule, right? That is a very tight constraint, and Planner lived up to that constraint. But it's provable that if you only have logic program where every computational step is justified by a computational rule, then you can't do true concurrency. So here's a limitation, and this might be fundamental to what Leslie was pointing out. So logic programming is not going to do it for us, okay? Because it's not going to do true concurrency, and there's a fundamental limitation. Thank you.
Was that
I would
a
like
question?
to, first of all, I'd like to just, I'm sorry, just a very quick comment. True concurrency is some kind of formalism. The statement that one kind of formalism can not do something of no interest. A formalism is a way of representing reality. Is interested in representing reality. It doesn't mean something in some other formalism.
So if you can't actually implement true concurrency,
it is a totally...
Leslie, you're breaking out.
Yeah.
So if you can't actually implement true concurrency, that's a serious limitation.
I mean, you can, I mean, if you step out of the purity of logic programming, I mean,
Then you have to define what you mean by logic programming. I gave a definition, you give one.
So if you, for example, take Prolog systems, I mean, they do have primitives for concurrency. Now you could talk about the semantics and stuff, but they are there nevertheless in Prolog. So you can write, concurrent program, so to speak, where you're waiting for certain variable to be instantiated and things like that. But there are built-in primitives that are given for that.
Yeah. My programming answer would be, I use logic programming to build the tools, but I'm not using it to model algorithms or concurrent algorithms. Quite often it's, in Horn-Clause logic, I find too much of a straitjacket. So there I prefer a language like TLA plus or the B language to express my systems and algorithms, but it all depends on what you're trying to achieve, right? Which language is most appropriate.
Well,
I hate to cut the conversation, but
I have a problem here that is, well, the time. So given that the last person that spoke was the guest of the session, we can conclude